Today topic is Fermat's theorem. Fermat's theorem states that if p is a prime and a is positive integer not divisible by p, then a power p minus 1 equivalent to 1 mod p. Okay, so here that is p is prime and a is positive integer not divisible by p. That means a is a relative prime to p. Let's see what is a relative prime. So relative prime is nothing but if two integers, so you consider two integers a, b, okay. So if GCD of a comma b equivalent to 1, then we can say that a, b are relatively prime numbers. Okay, relatively prime. Okay, so consider, and one more definition is there here. So the two numbers are relatively prime if they have no prime factors in common, that is their common divisor is 1. So here are two definitions for relatively prime. So one is the two numbers are relatively prime if their GCD is 1. Suppose you consider two integers a, b, GCD of a comma b equal to 1, then we can say both a and b are relatively prime. Okay, so here the two numbers are relatively prime if they have no prime factors in common. That means no prime factors. Okay, so no prime factors in common and their common divisor is 1. You know the prime number. What is a prime number? The number divisible by itself and 1. Okay, so you consider two numbers that is not having any prime factors in common, that is nothing but the relatively prime. Okay, consider one example for relatively prime. You consider 7 and 19. 7 equal to 1 into 7. Okay, so what are the divisors? What are the divisors for 7? 1, 7. What are the divisors for 19? 1, 19. The common one is 1. So we can say that 7 and 19 are relatively prime. Okay, so consider 8, 13. 8, 13. The common factors for 8. 1, 2, 4. Okay, so in order to consider that itself number. Okay, or if you consider also, there is no problem. 1, 2, 4. Okay, so next 18. 8 and 13. For 13, 1 and 13 only. So here the common is 1 only. GCD of 8 comma 13 is 1 only. Okay, so we can say both 8 and 13 are relatively prime. Okay, so next, come back to Fermat's theorem. Fermat's theorem. Here this Fermat's theorem states that p is prime and a is positive integer not divisible by p. Okay, so it is nothing but a is to be relative prime to p. A is relative prime to p. Okay, that is both a and p must be relative prime. Okay, so here we should prove that a power p minus 1 equal to 1 into mod p. Let's see the proof. So here consider the set of positive integers less than p. Okay, so positive integer sets, consider a set of positive integers that is less than p. We can say that the last number is p minus 1. Less than p in the sense p minus 1. So here 1, 2 and so on p minus 1. Okay, set of positive numbers representing with 1, 2 and so on p minus 1, and multiply each element by a. Multiply each element by a. That means here we are having the set of positive integers 1, 2, 3 and so on p minus 1. So we need to multiply this set with a. Okay, that is a, 1a, 2a, 3a and so on p minus 1 into a. Okay, modulo p. Okay, so first of all we need to multiply a with the set of positive integers, then we need to perform modulo operation with p. Okay, so here we got after multiplying each element by a. Okay, after multiplying each element of positive integers by a, that is a, 2a, 3a and so on, p minus 1a, we need to perform modulo operation. So that is a mod p, 2a mod p, like that p minus 1 a modulo p. Okay, so see here, to get the set x equal to a mod p, 2a mod p and so on, p minus 1 a mod p. Okay, so what is x? Here x is nothing but the multiplication of a with the positive integers, then performing modulo operation with p. Okay, so that is x set. Now we are having positive integers set, x set. Okay, so next, none of the elements of x is equal to 0. So here x is having a mod p, 2a mod p and so on, p minus 1a mod p, right? So this x contains, okay, none of the elements of x is equal to 0 because p does not divide a. So here x should not have 0. Okay. Okay, so is it clear? X is equal to, none of the elements of x is equal to 0. That means, so here in the definition already it said a is a positive integer not divisible by p. So p is a prime. So if it is divisible by p, then the remainder is 0. Okay, you consider here p, first one a mod p. If it is a is divisible by p, then it got p mod p. Then the result is 0. Remainder is 0. Okay, so now none of the elements of x is equal to 0 because p does not divide a. Hope you understand this point. Okay, next, no two of the integers in x are equal. Here are 2 points that x doesn't have 0 value. That means, so if you doesn't have a 0 value, why? Because p doesn't divide by a. Okay, so if you consider, if it is having a 0, that means it is having a 0. Okay, so remainder is 0. That is, so here the statement itself there, no, p a is not a is a positive integer not divisible by p. But okay, so here x is equal to 0. None of the elements of x is equal to 0 because p does not divide a. Okay, so p does not divide a, so that we should not take the 0. Okay, so x doesn't having 0 value. Okay, and one more point is here, no two of the integers in x are equal. Okay, so the values of x should not, no two integers in x are equal. Okay, so next statement is, so hope you understand these 2 points. So first one is x doesn't have 0 value, and second one is no two integers of x are not equal. Okay, so or no two of the integers in x are equal. Okay, so that means same values not be repeated. Okay, here assume that, so here these are the statements for proving to know the no two of the integers in x are equal. Let's see why the two integers are not to be equal in x. Okay, so assume that j equivalent to k mod p, where 1 less than or equal to j less than k, that less than or k less than or equal to p minus 1. Here observe 1 less than or equal to j less than k less than or equal to p minus 1. Okay, so we just assume that equation j equivalent to k mod p, where 1 less than or equal to j less than k less than or equal to p minus 1. Okay, because a is relatively prime to p. Okay, we can eliminate a, we can eliminate a from both sides of the equation. From the above equation ja equivalent to ka mod p, we can eliminate a. Then we got the equation j equivalent to k mod p. Yes. So next, whatever the equation we got after eliminating a, j equivalent to k mod p, it is not possible. Why? Because j and k are both integers less than p. Both are the positive integers less than the p. Please observe here the condition 1 less than or equal to j less than k less than or equal to p. Here observe that j less than k, so that it should not be equal j equivalent to k mod p. Okay. So if it is possible, if there is a multiplication with j and k, okay. So but here there is no multiplication of j and k here, directly j equivalent to k mod p, it is not possible. Okay. So next, okay. So next, we know, so therefore we know that the p minus 1 elements of x are all positive integers with no two elements are equal. Okay, this is the proof for why we should not take two values of x are equal. Okay, so next, we can conclude the x consists of the set of integers 1, 2 and so on p minus 1 in some order. Okay, so here 1, 2, 3 and so on p minus 1 as a new set of x. So the previous set of x is 1, 2, a mod p, 2a mod p, like that. So up to p minus 1a mod p, right? So by multiplying the numbers, so here multiplying the numbers in both the sets, so both the x sets, multiplying the both the x sets, we got this one. So a into 2a into p minus 1a, that equivalent to 1 into 2 into and so on p minus 1 mod p. So here by simplifying this equation, by simplifying it, we got a power p minus 1 into p minus 1 factorial, that equivalent to p minus 1 factorial into mod p. How we are writing p minus 1 factorial? 1 into 2 into 3 into and so on p minus 1. That means we can simplify it as a p minus 1 factorial. Okay, now we need to cancel p minus 1 factorial on both the sides if p is relatively prime. Okay, if p minus 1 is relatively prime to p, then we can cancel both the sides p minus 1 factorial. So here is the statement that if a and b equivalent to a and c, a into b equivalent to a into c mod n, then b equivalent to c mod n. That is here cancelling a on both sides if a is relatively prime to n. Here also same, if p minus 1 factorial. Okay, so if p minus 1 is relatively prime to p, then we can cancel p minus 1 factorial on both the sides. Okay, so here finally we got a power p minus 1 equal to 1 mod p. By cancelling p minus 1 factorial on both the sides, we got a power p minus 1 equivalent to 1 mod p. Okay, now look at the example here. So a equal to 7, p equal to 19. So we should prove that a power p minus 1 equivalent to 1 mod p. That is, here we have taken the a value 7, p value 19. Okay, now we need to prove 7 power 18 equivalent to 1 mod 19. Okay, so let's see here. So it requires that a be relatively prime to p. Okay, so here for Fermat's theorem, we should take a as a prime to relatively prime to p. Okay, so and when we can say the relative prime number, so here if GCD of a comma p equal to 1, then it is both a and p are relatively prime. So here how to calculate GCD of a comma p? Okay, so the factors of 7 or 1 7, factors of 19 or 1 19. Here the common factor is 1. Okay, so here, so that we can say GCD of 7 comma 19 is 1. Okay, so we can say A and P are relatively prime. Okay, so now we need to prove that 7 power 18 equal to 1 mod 19. Okay, so by substituting these A, P values in the above equation, we need to prove that. So here A power P minus 1, A value is 7, P value is 19, 7 power 18 equivalent to 1 mod 19. We should prove now. Okay, so here 7 power 18. Okay, we are considering 7 power 18 value like this. 7 into 60, 7 power 16 into 7 power 2. Okay, so now we need to calculate 7 power 2. 7 power 2 value is 49. Okay, it is equivalent to 11 mod 19. So if you do calculation that 49 mod 19, you got the remainder 11. Okay, so do calculation that. Okay, so 7 square equal to 49. If performs 49 mod 19, you got the remainder 11. Okay, so that here taking 11 mod 19. Okay, the value of 11 mod 19 also you got 11 only. Okay, so for that we are taking 11. Okay, so 49 that is equivalent to 11. Okay, next 7 power 4, that is we are considering 7 square into 7 square. Why we are taking 7 square into 7 square? 7 square into 7 square, that means 7 power 2 plus 2, right? So that is 7 power 4. Okay, so 7 square into 7 square, what is the previous value? 7 square value, here we got 11 mod 19. Now we need to multiply, that's 11 into 11, 121, that equal to 7 mod 19. Why we are taking 7 mod 19? So if you perform 121 mod 19, you got value near to 7. So here you take that values prime numbers. Okay, that is near to prime number. Okay, so next 7 power 8, 7 power 4 into 7 power 4, that is 49. Why we are taking here 49? What is the value of 7 power 4? 7. 7 into 7, 49. Okay, so for 49 the value 11 mod 19. Okay, like that we have calculated up to 7 power 16. Now the 7 power 16 value is 7 power 16 value 7 mod 19. We are taking 7 into 7 square value is 11 mod 19. Okay, we got 1 mod 19. How we are getting 1 mod 19? 77. 7 into 11, 77 mod 19. We need to perform 77 mod 19. Okay, so the remainder is 1. Okay, 1 mod 19. Okay, so next one, there is alternative for Fermat's theorem, that is if P is prime, A is positive integer. Here that A should not be a relative prime to P. So observe here, this form doesn't require A be relatively prime to P. Okay, so here both A is a prime and P is a prime and A is positive integer. Okay, you take any positive integer for A and P must be a prime number. So here for that the equation is A power P equivalent to A mod P. Okay, so look at the example here. A power P equivalent to, we should prove that A power P equivalent to A power P equivalent to A mod P. Okay, so here example, consider the value 5, A equal to 3. Here the prime number, you should take the P value prime number only, and here A you can take any positive integer here. Okay, not only the relative primes or prime numbers, so you should take you can take any positive integer for A value A. Okay, so here the equation is A power P equivalent to A mod P, right? So what is the value of A? 3. Okay, so the value of P is 5. Okay, 3 power 5 equal to 243, that equal to, so if you perform that 243 mod 5, you got the result 3. Okay, that's why here we are taking 3. Okay, you got when you performing a modulo operation with 5, 243 mod 5, you got the remainder 3. Okay, so that we are taking here 3 mod 5. Okay, so what is the 3 here? 3, the value of a. So we can replace this 3 with a. Okay, next mod p. P is nothing but, sorry, mod 5. 5 is nothing but p. Okay, so here a power p equivalent to a mod p. Okay, so hope you understand this Fermat's theorem. Okay.